Yeah, good morning all of you. I welcome you all to this fourth lecture on basic calculus. So right now in yesterday's class, if you quickly encapsulate last day classes, we have been looking at the concepts of limits, and then after we discussed what's continuity of a function in our second lecture probably, and what we have discussed what could be the differentiation, and we have seen different differentiation techniques to solve or to analyze derivatives of different functions. Then we have discussed the concepts of mean value theorems, and we have seen what's the geometrical essence of this mean value theorems, and we have discussed the three mean value theorems, namely Lagrange's mean value theorem, Rolle's mean value theorem, and Cauchy's mean value theorem in yesterday's class. And we have solved few gate questions that appeared with by looking at the different techniques. So in today's class, basically, I would like to start my discussion with Taylor series, and then after we would like to visit a very important concept for gate as well as other exams, the concept of maxima and minima. Okay, there's nothing difficulty at any place, but the only thing you need is to follow the class straight away. Okay, so let us start our discussion today. So first of all, we'll start our discussion with Taylor series. And of course, we have been discussing a lot of times that this Taylor series is really important in mathematics, because this Taylor series gives us all the expansions of functions. So for example, if you see, we have written the expansion of e power x as 1 plus x by 1 factorial plus x squared by 2 factorial and so on. Basically, that series could be evaluated from this Taylor series. Similarly, the expansions of different functions like sine x, cos x, all these functions are also evaluated here. Okay, so I'm straight away giving the Taylor series denotation for you without discussing the generalized mean value theorem, because that's not of much importance in this particular course. So let me write the Taylor series. If f of x is continuous and differentiable in x comma x plus h, basically this is the interval, and f dash of x comma f double dash of x comma f triple dash of x and so on are all continuous in x comma x plus h, then the function f of x plus h, is given by, now I am writing the Taylor series expansion, which is of very much importance. Please take it carefully. F of x plus h is equal to f of x plus h into f dash of x by 1 factorial plus h square by 2 factorial into f double dash of x, plus h cube by 3 factorial into f triple dash of x and so on. So basically, this is how Taylor series expansion gets evolved for a given function f of x, provided all these differentiations f dash of x, f double dash of x, f triple dash of x, all these derivatives should continuously exist. For example, if you see e power x, the differentiation of e power x is e power x, means how many times you differentiate e power x, it doesn't matter, these derivatives are continuously existing. So basically, this is the expansion of any function f of x within this interval x comma x plus h, and we generally derive any of our series expansions using this particular formulation that I mentioned in this box. Okay, so I'll give you a moment, and who joined late, please take this notes. So yeah, I'll give you a moment to take this. Good morning all of you. Good morning Divya, Bhavana and all. Please take these notes. Okay, we'll be going ahead in a soon way. Actually, there's a clear background for this where we see generalized mean value theorem, but right now I'm not discussing that in this course, but straight away giving you the expansion of this f of x plus h, which is of need for us. Good morning, Evan. Is it visible to all of you, and am I audible to all of you? If yes, please write down S over there in the comments. Is it clear and audible? Okay, thank you all. Good morning, all of you. Okay, so shall we move ahead now? So the expansion that we have is f of x plus h is equal to f of x plus h by 1 factorial into f dash of x plus h square divided by 2 factorial into f double dash of x plus h cube by 3 factorial into f triple dash of x and so on, things like this. This is what we have seen now, correct? So if you make a small analysis here, for example, as h tends to 0, means if h is very small, that's what I mean to say. If h is very small, now see one thing, if h is very small, can I neglect this h square, h cube, all these higher order terms? Because in previous class also we are discussing, when h is very small, the higher powers of x keep on decreasing to values which are very low. So in that case, if I approximate this, and if I take in particular linear approximation, the meaning of linear approximation is considering the terms only up to the degree of h to be 1. Means I'll consider this is only till this particular point, because if you see the degree of this h is 1, and you know equations or functions of degree 1 are called linear polynomials or linear functions. So linear approximation means considering only till here, basically to the order of h. If you say, then this series gets reduced to f of x plus h is equal to f of x plus h by 1 factorial into f dash of x, correct? So if I make slight modification, if I bring out this f of x onto the left hand side, we have f of x plus h minus f of x is equal to h into f dash of x. So this implies f dash of x is equal to f of x plus h minus f of x divided by h. Of course, this is the formula when you approximate this to linear approximation, and you can apply only linear approximation if h value is very small. And if h value is very small, I can always write this limit h tends to 0 here. And if you see, this is the first principle of differentiation that we obtained while defining the definition of differentiation or derivatives, correct? So please take this when you'll obtain this first principle of differentiation from this Taylor series when you apply for a linear approximation. Okay, please take this. You can name this. This is first principle of differentiation. Okay, please take this. Okay, Manoj, I'm explaining once again. After considering h is small. If h is very small, then h square value is still more smaller. Correct? For example, if h is 0.1, then h square will be 0.01, correct? Which is very much smaller. And dividing such smaller numbers by higher factorials will further reduce the values to very less value. So I'm neglecting the terms which are here, or basically I'm neglecting higher orders of h. So if I neglect higher orders of h, then this particular part which is here is nothing but this. Okay, am I clear, Manoj? Okay, taken? Clear? Now, let us move ahead. So see here. So if you consider this Taylor series, we have this Taylor series as f of x plus h is equal to f of x plus h by 1 factorial into f dash of x plus h square divided by 2 factorial into f double dash of x plus h cube divided by 3 factorial into f triple dash of x plus and so on, like this. Now if you replace this x and h with some particular values, then we could get something. See here, put x is equal to a and h is equal to x minus a in above equation. If you see, this is an equation of f of x plus h. So if you replace x by a and h by x minus a in this equation, let us try to see what the new form or new looking of this Taylor series. In above equation, then this implies, look here carefully, f of, if I am replacing x with a plus I'm replacing h with x minus a. I'm replacing h with x minus a is equal to, here there is f of x. So the series is f of a plus h can be written as x minus a into, instead of this x we can put a again. So f dash of a by 1 factorial, because this 1 factorial which is in division here can be written here. It's obvious thing that you know, x minus a whole square in terms of this h square into f double dash of a by 2 factorial plus x minus a whole cube into f triple dash of a by 3 factorial plus and so on. This is an infinitely extending series. Okay, since Taylor series is an infinitely extending series, and depending upon the value of h, we will decide how many terms to consider till which degree. Okay, so this is, if you simplify this a bit, we have this a gets cancelled. So f of x is equal to f of a plus x minus a into f dash of a by 1 factorial plus f double dash of a by 2 factorial into x minus a whole square and plus f triple dash of a divided by 3 factorial. Let me write this 3 clearly. 3 factorial into x minus a whole cube plus and so on. So this is how Taylor series look like when you expand a function f of x about the point a. The meaning of this is, if you want to expand this function x in terms of expansion having the terms x minus a, then this is how you expand any function. So let me put it in a box. Okay, so this is basically expansion of Taylor series, expansion of any function in Taylor series about this point a. Okay, so please take this. These are actually 2 different forms of Taylor series. This is the generalized form in terms of x and h. This is at a particular point expansion at the point a. And let me assume that all these derivatives, f dash of a, f double dash of a, f triple dash of a, all these are existing. As in case we have assumed this f dash of x, f double dash of x, all these things exist. Okay. Okay. Now, taken. Now, the expansion of Taylor series we have is f of x is equal to f of a plus x minus a into f dash of a by 1 factorial plus x minus a whole square into f double dash of a divided by 2 factorial plus x minus a whole cube into f triple dash of a divided by 3 factorial plus and so on like this. Correct? This is what we have seen now. Now, if you see little thing, if expansion of function is about the point x is equal to 0, point x is equal to 0 means basically when you evaluate in this particular format, you will be getting the series in terms of x minus a. Correct? We have x minus a terms all over in this series. Now, if we expand about a is equal to 0, we will be having the series in terms of x only. Correct? So, which means then this series gets converted to f of x is equal to f of 0 plus x minus 0 into f dash of a by, f dash of 0 again. So, f dash of 0 divided by 1 factorial plus x minus 0 whole square into f double dash of 0 divided by 2 factorial plus x minus 0 whole cube into f triple dash of 0 divided by 3 factorial and so on, things like this. Correct? So if you see, if you write a moment, f of x is equal to f of 0 plus x minus 0 is x into f dash of 0 divided by 1 factorial plus, here it is x square. So x square, about point a is equal to 0. X square by 2 factorial into f double dash of 0 plus x cube by 3 factorial. Correct. About the point a is equal to 0. Okay. So x cube into f triple dash of 0 plus and so on. So this is how your Taylor series gets looked when you expand the function about this particular point. So now this particular series means that basically the expansion of Taylor series about the point A is equal to 0 has got a specific name which is called Maclaurin series. This series is called Maclaurin series. So basically Maclaurin series is nothing but a special case of Taylor series when you expand the function about the point A is equal to 0. Okay. Okay, taken. This Taylor series is actually very easy to remember because the terms are very of similar pattern, but this series is really of very much importance, which you will see shortly in this class. Okay. Am I clear to all of you? Am I audible? And everything going fine? Okay, thank you all of you. So see here, we'll continue. Now we'll see why the expansion of e power x is 1 plus x by 1 factorial plus x square by 2 factorial and all these things. And last day someone was asking me, when e power x is a polynomial, then the differentiation of e power x should be a polynomial of degree less than 1. But again, why it is again e power x? We'll see now. Okay, so see here. Let us consider let f of x is equal to e power x. For example, e power x is the function for which you need to know the series, okay, in terms of x. So f of x is equal to e power x. Then the expansion of Taylor series, then the expansion, or you can write then the Taylor series expansion, better. Then the Taylor series expansion of e power x about the point A is equal to 0 is given by look here. Yes, that's the Taylor series expansion. Let us see how that's coming now. We have f of x is equal to f of a. I mean, directly, since we are putting a is equal to 0 without an extra step, I am writing here f of 0 plus x by 1 factorial into f dash of 0 plus x square by 2 factorial into f double dash of 0 plus x cube by 3 factorial into f triple dash of 0 and so on, things like this. Okay. So now if you see what is f of x that we have, if you see here, f of x is e power x. And we know how many times you differentiate e power x, that doesn't matter, the function retains again. So f dash of x is equal to e power x, f double dash of x is also e power x, and this series goes on like this. Okay, so, the sequence goes on like this. So this implies e power x is equal to, because our function that we are taking is e power x initially here, so e power x is equal to f of 0. If you put x is equal to 0 in this particular place, we have e power 0. And what's the value of e power 0? Since e is a non-zero constant, you have it is 1 plus x by 1 factorial into, now what is f dash of x? F of x is e power x, so which means f dash of x is also e power x, which means f dash of 0 is again 1. E power 0 is 1 plus x square by 2 factorial into, again doesn't matter, since all these functions are e power x, we have all the derivatives as 1 at x is equal to 0. So into 1 plus x cube by 3 factorial into 1 plus x power 4 by 4 factorial into 1 plus and so on, things like this. Correct? So this implies e power x is equal to 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial and so on, things like this. Okay, so this is how the expansion of e power x looks like this. So in the first class, if you remember, I mentioned you the value of e is 2.71 around, correct? So how to get that now? If you put x is equal to 1 in both sides of this equation, you could get, after some particular number of 4 to 5 terms, you will get some very smaller terms, because the division is 1 by 120, 1 by 6 factorial, 1 by 7 factorial and all these things. So you'll end up with the value of e to nearly 2.71. Okay, so please take this. And once we write this, we'll see the expansion of sine x. Okay. This is 2. Okay, please be careful. Okay, taken. So now see here. Now, what if f of x is sin x? F of x is equal to sin x. Now see here carefully. If f of x is sin x, what is f dash of x? Cos x. Correct? Then this implies what is f double dash of x? Means basically what's the second derivative? Derivative of cos x is minus sin x. Correct? We have seen. Then f triple dash of x is again derivative of this f of f minus sin x is minus cos x. And what's the fourth derivative of this? Minus cos x derivative is, see, derivative of cos x is minus sin x, and since there's a minus sign over, we have plus sin x. Okay? So if you see now, this sin x and sin x is same here, which means if you differentiate this here again, you will be getting again cos x. If you differentiate that again, you will be getting sin x, which means these four terms are basically repeating. Correct? So therefore, if you write the expansion, we have f of x is equal to f of a or f of 0. If you write directly without an extra step here, f of 0 plus f dash of 0 into x by 1 factorial plus x square by 2 factorial into f double dash of 0 plus x cubed by 3 factorial into f table dash of 0 plus x for 4 by 4 factorial into f fourth derivative of 0 plus and so on, things like this. Correct? Now if you see, if you put x is equal to 0 here, what is f of x? Sin x. Basically that's what we have assumed here. So sin x is equal to f of 0. If f of x is sin x, what is f of 0? Sin 0. And what's the value of sin 0? It's 0. Correct? So 0 plus, now f dash of 0. What is f dash of x? So basically if you want me to write, we have f of 0 is equal to 0. Then f dash of 0 is equal to, if you put x is equal to 0 here, cos 0 is 1. Correct? Then what is f double dash of 0? If you put x is equal to 0 here, we'll get again 0. Then what is f triple derivative of 0? Here again if you put, you'll be having minus 1. Correct? Similarly, f fourth derivative of 0 is again 0. Means basically if you see, when these four terms are getting repeated, this coefficient 0, 1, 0, minus 1 gets on repeating. Correct? Which means here we have f dash of 0 as 1. So 1 into x by 1 factorial plus then even the derivative, second derivative is again 0. So 0 into x square by 2 factorial plus third x cube by 3 factorial, which I have already written there, into what's the third derivative at 0? Again we have minus 1 plus, and this series goes on like this. So which means if you see a bit clearly, we have sin x is equal to, now see one thing clearly, here all the even the derivatives are 0, means second derivative, fourth derivative, similarly sixth derivative, eighth derivative, all these derivatives are zeros because this sin and cos x keep on repeating alternatively, of course with a plus and minus alteration. So which means all the even the derivatives are 0 and all the order derivatives are of magnitude 1 with signs being changed after every successive term, which means here if I have plus sign for x, then even coefficient is 0. Again for odd coefficient I have minus 1. So minus x cubed by 3 factorial. Again fourth derivative will be 0 and fifth derivative will be 1, of course with the sign changing from here. So that is plus x power 5 divided by 5 factorial. Again sixth derivative will be 0 and again seventh derivative will be, coefficient of seventh derivative will be minus 1 because there is a plus 1 here, so next would be minus 1. So minus x power 7 by 7 factorial and so on. So this is how we get sin x expansion in terms of x, and this is what I mentioned earlier when I was about to show you limit x tends to 0, sin x by x is 1. Correct? So this is the expansion of sin x. So with the help of this knowledge, okay, Sandeep, I'll explain that why differentiation of e power x is again e power x. See here. So this is the expansion of sin x. So basically with this knowledge I gave you, could you try expansion for cos x and tell me the answer? What's the expansion of cos x about the term x is equal to 0? Why derivative of e power x is e power x? See here. If you see expansion of e power x is 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus x power 4 by 4 factorial plus x power 5 divided by 5 factorial plus and so on, things like this. Correct? Sandeep, now see here. If you differentiate this with respect to x, d by dx of this e power x is equal to, what's the derivative of 1 with respect to x? 0 plus this 1 by 1 factorial is a constant. So 1 by 1 factorial into differentiation of this x is 1 with respect to x plus this 1 by 2 factorial is again constant here. So 1 by 2 factorial into derivative of this x square is 2x. Correct? Plus this 1 by 3 factorial is again common here. So one constant here. So 1 by 3 factorial, if you take it out, derivative of this x cube is 3x square plus again this 1 by 4 factorial is a constant. Differentiation of x power 4 is 4x cube and so on, things like this. Correct? So if you see, if you have n by n factorial anywhere, you can write this n by n factorial as n factorial can be written as n into n minus 1 factorial, because you know 5 factorial can be written as 5 into 4 into 3 into 2 into 1, which is same as 5 into 4 factorial. So if there is n factorial, this n factorial can be written as n into n minus 1 factorial. So when you cancel this n, you have this n by n factorial as 1 by n minus 1 factorial. Correct? So if I apply this logic here, d by dx of e power x is equal to 1 by 1 factorial, which is 1 plus, so 2 by 2 factorial, which is n by n factorial. This can be written as 1 by n minus 1 factorial. So if n is equal to 2, this will be, this 2 by 2 factorial will be 1 factorial, 1 by 1 factorial into x plus again this 3 by 3 factorial will give you 1 by 2 factorial into x square plus again 4 by 4 factorial will give you 3 factorial, 1 by 3 factorial into x cube plus and so on like this. So if you see, this is nothing but 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial and so on, things like this, which is the same as the expansion of e power x. And so that's why the derivative of e power x and the function e power x both are same. Okay. I hope I cleared you, Sandeep. Yeah, alternative signs because of this minus sign getting repeated in sine functions. Okay, so basically I hope you have worked out. So I'm directly giving you what is the expansion of cos x about x is equal to 0. Cos x is equal to 1 minus x square by 2 factor x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial and so on, things like this. Okay, so now if you see, I told you one more thing, why cos 0 is 1. Now yourself, if you put x is equal to 0 in this equation, no, it's of even terms actually, it's 1 minus x square by 2 factorial. Okay, please check it correctly, Sai once. This is the actual expansion that you get for cos x. Now, why cos 0 is 1? If you put x is equal to 0 in this equation, you will get yourself to know why cos 0 is 1. Okay, cos 0 is equal to 1 minus and all these terms are, it's now zeros. So cos 0 is equal to 1. Okay, so basically this is how we'll write Taylor series in particular for any function, provided the functions are differentiable. Okay, so along with this, I would like to give you two more expressions, two more expansions for functions. See here, when mod x is less than 1, 1 plus x whole power minus 1 is equal to 1 minus x. Okay, let us put plus 1 here. So you'll have things x square divided by 2 factorial plus I'm sorry for this, there is no 2 factorial here. 1 plus x square plus x cube plus and so on. This is an infinitely extending series. Similarly, this is same as, this expansion is also same as 1 minus x whole power minus 1. Okay, so all these things, both these are having similar expansions. So similarly, 1 minus x whole power minus 2 is same as 1 plus 2x plus 3x square plus 4x cube and so on, things like this. Binomial expansions, basically if you see in class 11 and 12 you will be getting this, but sometimes it's good to have knowledge of them. Okay, so I hope there is nothing much difficulty in this particular part. So we have straight away given this as cos x. Okay, so see here, next we will discuss the concept of maxima and minima with the help of this. And before straight away going to concept of maxima and minima, I'd like to show you how L'Hospital rule came. Okay, because we have seen this L'Hospital rule is really important for us in dealing limits of the form 0 by 0 or infinity by infinity. Correct? So we'll see how this Taylor series, from this Taylor series, how this L'Hospital rule got evaluated. So for example, if you see, we have limit x tends to a, f of x divided by f of a is equal to f dash of a divided by, this is g of x is equal to g dash of a if f of a is equal to g of a is equal to 0. Correct? Because if you get this x tends to a, then this f of a and g of a, if both are giving zeros, then you'll be getting 0 by 0 form. So you have f dash of a divided by g dash of a. Okay, so if you see now, here, what is the expansion for f of x in Taylor series about the point a? F of a plus x minus a into f dash of a divided by 1 factorial plus, just let me go to the minus side. Did I put pluses here instead of minus? Okay, I'm sorry for this. These are minus actually. Please make a note here. This is minus 1. Okay, that's what I have it in there. Just sorry for, thank you for cutting me. So see here, let us continue here. X minus a into f dash of a by 1 factorial into x minus a whole square into f double dash of a by 2 factorial and so on, things like this. Similarly, g of x is equal to g of a plus x minus a into g dash of a divided by 1 factorial plus x minus a whole square into g double dash of a by 2 factorial plus and so on like this. Correct? Now, if you divide these two functions, basically, it means if you apply this limit x tends to a, f of x divided by g of x. Now, if this condition is getting satisfied, means if f of a is same as g of a, and if both of these things are zeros, then you got f dash of a by g dash of a. And now we'll see how. See here, if I'm writing this series, and if f of a is equal to 0, can I write this series excluding this term? Means if I remove f of a from this particular expansion, then can I continue the series from here since f of a is already 0? So we have x minus a into f dash of a, of course there is 1 factorial here, plus x minus a whole square by 2 factorial into f double dash of a plus and so on, things like this, divided by what would we have in the denominator similarly? X minus a by 1 factorial into g dash of a plus x minus a, x minus a whole square by 2 factorial into g double dash of a and so on, things like this. So now if you take one x minus a common both from numerator and denominator, you'll be having this x minus a common, then you'll be having this square cut and all these things. So when you put x is equal to a here, all these terms from here, from the second term will get to 0 because every term will have an x minus a involved here. So when there is x minus a involved in every term, when you put x is equal to a, all these terms from the second term goes to 0. And that's the same case with g of x is equal to 0. And the thing you are left with is f dash of a divided by g dash of a. Correct? So this is how this L'Hospital rule was obtained, and this is really useful for evaluating limits of form 0 by 0 or infinity by infinity in our basic calculus. Okay. So please take this. And if you have any points, you can ask over there. See, I'm not considering these terms because it extends to a, all these terms are zeros. Okay, so that's why. So this is how basically you will evaluate L'Hospital rule based on this Taylor series. Okay. I hope all of you are taking these notes. Mod x less than 1 expansion, please explain, sir. Okay, see here. Meanwhile, whoever is here, please pause this and take these notes. I am revisiting back to the state. See, we have a geometrical series. For example, if you have the sequence A, AR square, which is of course called geometric progression. Geometric progression, which you study in your class 10, hopefully, I hope. So if this is the geometric series, now if you calculate the sum of n terms, first n terms means a plus ar square plus and so on plus a into r power n minus 1. If you evaluate all these things, then basically the sum of first n terms is given by a into 1 minus r power n divided by 1 minus r. This is what the formula I have for expansion of, sum of n terms of this geometric progression. Now see carefully one thing. When modulus of r is less than 1 means if r is a value which is lying in between -1 and 1 means basically r is a value of decimal like 0.9, 0.8, all these things, and n tends to infinity. And n tends to infinity means if r is very small means basically if r is less than 1 and if n is very large number, then this value r power n tend to 0. If these are the cases, when mod r is less than 1 and n tends to infinity. Hi, good morning all of you. Please join and quick look soon. So when mod r is less than 1 and n tends to infinity, this r power n is less than 0, because I have told you, suppose if r is 0.5, then r square is 0.25 and r square is 0.0625, which is very smaller than that. So finally, when n is very large, we'll get this r power n very close to 0. So which means we have sum of infinite terms of an geometric progression is equal to a by 1 minus r, where r is the common ratio that is involved here. So if you look at this series now, it's extending infinitely terms, and I have told you this common ratio is basically this x is the common ratio between every term in this series, and when mod x is less than 1, like this, when mod r is less than 1, the expansion of this series is a by means first term divided by 1 minus r, and if you see the common ratio r is x in this case, which is same as 1 minus x whole power minus 1. Clear? So that's how basically this expansion is 1 minus x whole power minus 1. Okay. Clear? I'm going back again to our discussion, formal discussion. So this is how L hospital looks like. L hospital. Okay, and this is how you'll get. No, Monica, see here, if f dash of a and g dash of a are 0, then we get f double dash of a by g double dash of a. Correct? I told you if both, again, if this is also giving 0 by 0 form, then we'll again differentiate the functions. And this is again f double dash of 0 by g double dash of 0. This is what we have seen in Taylor series. In L hospital, again, you can visualize from here. Okay. Correct, Monica, what you are telling is correct. If f dash of a and g dash of a are 0, then again we'll be having f double dash of a divided by g double dash of a. Because this L hospital is the name of the person who dealt with this particular things. Okay. Or maybe he couldn't find a good name like you, Mohan Dev Gandhi. Okay. So that's why he is named such way. So see here. Now we look at the concept of maxima and minima, which is really important in calculus as well, and later in advanced courses this concept of maxima and minima is really important, because if you want to perform something, you need to know what's the maximum effect given by that and what's the minimum effect given by that. For example, in mechanical, if you see, like if you design an engine, you need to know what's the maximum efficiency for that. If you are a civil engineering person and if you are dealing with beams, you need to know what's the maximum bending moment and all these things. Similarly, if you are from computer science or some other background, you need to know what's the maximum life a computer or a hard drive can have. So this concept of maxima and minima is really important in our day-to-day lives. So for that, we should start building up a background. Okay. So see here. Concept of maxima and minima. So basically in today's class, I'll confine myself to in learning the concepts of this maxima and minima, and by tomorrow we'll be looking at some questions that were asked in GATE examination. Okay, and then we'll see how to approach different kinds of questions that appear. Okay, so let us see here. To discuss the concept of maxima and minima, let me introduce you one very important big concept, which is increasing and decreasing functions. Increasing and decreasing functions, because this concept is really important and questions came even in GATE examination from this. They'll give you a function and they'll ask you which of these functions is increasing, which of these functions are decreasing. And you know, I'm quite advising you that many times you'll be given functions which are not known to you. For example, if they give you e power minus x into x squared plus 1, for which you don't know the graph, then how you'll decide how a function is increasing or decreasing? So let us try to see such backgrounds that are involved here. Increasing and decreasing functions. First of all, let me deal with the first fellow, increasing function. Increasing function. Now see here carefully. A function f of x is said to be an increasing function. Is said to be an increasing function if f of x increases as x increases. Means if you are increasing a value of x in that function, that f of x should also increase. For example, if you take e power x, then you know e power 1 is e, and e power 2 will give a higher value since the value of a is more than 1. So likewise, if you keep on increasing this value of x, the value of this outcome keep on increasing, correct? So, but practically if you see, for all the functions this might not be the case. So we'll define one more definition for this increasing function, but this is the actual basic ideology. Like if you see a function like this, 0, x, y, then if you see some function like this, you can see here as x is increasing, y is also increasing. So basically this is your y is equal to f of x, and it's an example of increasing function. Increasing function. Okay, so basically this is the thing. Monotonic all we'll discuss later in a moment. So Rahul, so please for the time being, right now concern here increasing function. So we can define increasing function in another way, as some of you are already mentioning. A function, correct, what you have told is correct. A function, Monica, a function f of x is increasing, is said to be increasing, otherwise that would make a better sense, is said to be increasing if f of x1 less than or equal to f of x2 for all x1 less than x2, and strictly increasing if f of x1 is less than f of x2 for all x1 less than x2. If you see, the basic difference between these two is I have removed this equality sign here, because if you want to be strict, you don't allow such any leisures over here. So let me see one thing. Now, one thing I have written, f of x1 is less than f of x2 for all x1 less than x2. So which means, can I write, this implies f dash of x is greater than, less than 0. Sorry, this is greater than 0 actually, because let me show you why this f dash of x is greater than 0. Okay, for the function to be increasing. Let me first set up this axis. I'll show you why this function f of x, f dash of x has to be greater than 0 if the function has to be increasing. Okay, so 0, x, and this could be my y-axis, which I set up here. So if you see now, this is y is equal to f of x. Y is equal to f of x. Correct? So see one thing clearly. Let me use this. Now let me show you. I think red is visible for you. I hope it should be visible. Okay? Or let me use another color. Let me use this green, so you could see things. Okay. So for example, if this is my x1, then this is my f of x1. Correct? Now if this is my x2, this is f of x2. Correct? Now see one thing, if I consider this product delta y by delta x, which is basically the differentiation when dx is very small, we have f of x2 minus f of x1 divided by x2 minus x1, correct? And if you see, since this f of x2 is on the top of f of x1, means if this f of x2 is above f of x1, then this value f of x2 minus f of x1 is a positive value, correct? That's what you could see easily. Divided by, similarly, if x2 is more than x1, this x2 minus x1 is also positive. So both these are positive terms, and the ratio of two positive quantities is again a positive quantity. Okay, so which means this difference is basically, if you want to talk at a particular point, then this difference is very small, and we are able to talk at a point. So this implies this f dash of x is positive, means for the function to be increasing like this, the function should have a derivative positive. Geometrically also we can show the same thing. If you remember a bit geometry that we are dealing with, let me use this. So for example, if this is the point of interest when these two are tending to each other. Now if you draw a tangent here, for example, let me draw it carefully once. Okay, I hope I'm not clear here. So for example, if you try to generate a tangent like this, which is of course cutting this, touching this curve here, this angle theta that you see, this theta is less than 90, correct? So if theta is less than 90, what about tan theta? Theta is in first quadrant, so tan theta is positive, correct? Which means slope at this point is positive, which means the derivative at that point is positive. So for a function to be increasing like this, you should confirm that slope of a function is positive or not. Okay. So for any function, whether the functions are positive or negative, then you can see this f of x is increasing or decreasing. Delta y by delta x and dy by dx. Basically, you consider delta y and delta x when the difference between x is very large, and you consider dy by dx when this difference is very small. And since we deal slopes, I have pointed a point here, which is when these x1 and x2 tend to each other. Okay. So please take this. So tomorrow we'll be really looking at some important or some really good questions that came in GATE from this concept of maxima and minima. So with this background that I gave you, could you define for decreasing functions and could you write up the things? I'll give you a moment time, so please write that, and I'll continue after I see your options. Your comments. Okay. So please try the definitions of decreasing functions and please try to get this graphs and all. Yes, Monica, it's correct. If x1 is less than x2, then f of x1 is greater than f of x2. Could you give an example for that? Any one of you for decreasing functions? E power minus x, correct, Krishna? So please provide material. Okay, we'll work on that. E power minus x, all of you are correct. 1 by x, okay, correct. E power minus x, 1 by x. Cos x. Cos x, there is a special case. We'll see, Pavin, why cos x is not, we can't say it's completely decreasing. Cos x is also increasing in some part of the interval. We'll look at that concepts also. 2 by x, yeah, I got a lot of examples. All of you are correct. So which means the decreasing functions, if you want to define, we could look into something like this. I hope you can see this blue color without any issue. Correct? Decreasing functions. A function f of x is said to be decreasing. In x if f of x1 greater than f of x2 for all x1 less than x2. Or you could write it in other way also. If you see, if f of x1 is less than f of x2 when x1 is greater than x2. That's the obvious sense that makes it. So this implies f dash of x is less than 0. Okay. And examples, if you see, as many of you are writing now, Yeah, Rahul, you gave a nice example, log x a for a greater than 1. But I think it should be, a less than 1. Please make a correction over there. So first example is, e power minus x could be a good example always to show you a decreasing function. And second could be something like cos x in 0 to pi by 2. Okay. You should mention this interval. Okay. Rahul, I hope now you got the things right. And log x to the base a when 0 less than a less than 1. I have given you graphs of these three functions, if you remember. So you can check. If you see, the graphs look something similar to this. Now, if you want me to show you this derivative, negativeness of this derivative in graphs, you can see here 0, x, f of x, or y, basically, which is f of x. So now, if you see, the function could look something like this. Correct? As x increases, this f of x decreases. Okay. Basically, you see the graph of 1 by x and e power minus x could all look in similar in shape. Correct? So now, if you plot two particular values here, x1 and x2, then this is f of x1 and then this is f of x2. If you see, this condition is getting satisfied for x1 less than x2. If you see here, x1 is to the left of x2, which means x1 is less than x2, f of x1 is greater than f of x2. And if you see, f of x1 is on the top. Okay? So which means, if you consider this dy by dx, when this difference is very small, let us assume that x1 and x2 are very close, but for your image understanding, I have enlarged them. So difference is f of x1 minus f of x2 divided by x2 minus x1. Or else, since we follow the same notation here, we can write x1 minus x2, because we write y2 minus y1 divided by x2 minus x1, or y1 minus y2 divided by x1 minus x2. Okay, this order should be same. So if you see, since f of x1 is on the top, this value of numerator is positive. And if you see here, since this x1 is to the left of x2, this product, this difference x1 minus x2 is negative. Yeah, f dash of x is negative now. Correct. So positive value divided by negative value would give you a negative sign. So which means this dy by dx, basically you're talking, is negative, and that shows this differentiation f dash of x is less than 0. Okay. Geometrically, if I want to show you the same thing, I could write these things for you. So for example, let us suppose here is the point. If you see, I hope you can see the things here. Yeah. Here, now if I draw a tangent somewhere here, which is passing like this, now if you see, this angle made with x-axis in positive sense is theta, and theta is here greater than 90. Basically, it's falling somewhere in the second quadrant, and in second quadrant, tan is negative. So this implies tan theta is negative. I mean, tan theta is negative. Okay. So this is how you will see for decreasing functions, means for all these cases, the tangent will be making an angle which is more than 90, and in general it shows the decreasingness of these functions. Okay, so this is the background of increasing and decreasing functions, and this is how you decide the functions are increasing or decreasing. And we'll work out quite a few examples in this case in tomorrow's class for a better understanding. Okay, so please take this. If you understand these concepts, please write yes in the comments. If you don't understand or if you have some difficulty, please ask me. I'll repeat again, because these two concepts are really important for the background of Maxima and Minima. Okay. If you all understand, please put a comment yes in the comment box. Okay, I hope all of you have understand. You have put in the comments yes. Thank you. So please stay tuned. We'll go for next part. So I want to explain log x. If you see, I have given you the graph of this function in the first lecture, if you see, and I asked you, this log x graph is also very important for interviews because of this differenceness in nature. Okay? So please, Praveen, I suggest you to go for first lecture, and please, Mohandev, why can't we measure angle in anti-clockwise? Actually, we are measuring anti-clockwise. down if theta is 90. See, tan theta is sine theta by cos theta, and if theta is 90, the differentiation gets not defined, so we can't comment on the nature at that particular point. We'll see in concept of minima, maxima and minima, there are some things called points of inflection and all these things we'll discuss there. Okay, like because it was taken in a like convention to take measure things in anti-clockwise sense. That's it. That could make only difference, and all the trigonometric basics that were mentioned with respect to anti-clockwise sense. Okay, Mohandev. If you are so much interested, you could develop a theory with clockwise sense again. Then your first quadrant could be the fourth quadrant. Okay. So right now, moving from here, now we'll see one important thing. If a function f of x is either increasing, or I may confuse you here, so let me consider only the word increasing here, is increasing for all x belongs to R, means on complete real number plane, if the function is increasing, then we say f of x is monotonically increasing. Someone was asking what's the definition of this term monotonically. Monotonically increasing means the function over the complete real number domain, it has only single nature. For example, if you take e power x, e to the power x. Now, if you see this graph of this function, the graph is looking like something like this. Means on this complete real number plane, this function is continuously increasing, because from minus infinity to plus infinity, meanwhile at any point, if you start increasing your x, your f of x increases. But there are some functions which are not of this particular nature. Means they'll be increasing in some part of the real numbers, in some interval of the real numbers, and again it will be decreasing in some interval of the real numbers. Okay. For example, if you say, functions that are non-monotonic. Example, sine x or cos x you can take considerably. Now, for example, if you trace the graph of sine x here, let me shrink this screen a bit. I hope still you can see the things clearly here. Or let me increase a bit slightly for your comfort. Okay. So now if you see sine x, correct. So if you see sine x, 0, x, y, I'm drawing only one half of the loop. For example, if this is the case, something like this, then this is x is equal to pi by 2 and x is equal to pi. Now if you see from x is equal to 0 to pi by 2, this sine x, this function is basically y is equal to sine x, or f of x is equal to sine x. So if you see, this sine x is increasing in between x is equal to 0 to x is equal to pi by 2, correct? Because from x is equal to 0 to x is equal to pi by 2, if you keep on increasing your x, your f of x keeps on increasing. But there comes a point where after pi by 2, if you keep on increasing x, this function again starts decreasing. So there are two kinds of functions which are monotonic in nature. Of course, it can be an increasing or decreasing, but it's monotonic. It has only single nature. Then we have some functions which are of this format, which are not monotonic. Okay, so please look at these things once. You can take a note of this, quick note. I hope everything is going fine as of now. Correct? It's been already 1 hour since we started the lecture. So please stay attentive. When about tan x. Tan x is always an increasing function in general, but of course not at odd multiples of pi by 2, because at odd multiples of pi by 2, this derivatives does not exist. Means basically you can't decide f dash of x is greater than 0 or less than 0. Okay. Okay. So see here, I'm giving some time to write notes. If you want, you can take, or if you can pause the video. Because for the first 2 videos, you're asking me to give me some time for notes taking. Okay. So now, procedure to find maximum and minimum of a function. Okay, so now how will you decide whether a function, how will you find whether, the maximum and minimum value of a function? See here, let f of x is the function, then first point, equate f dash of x is equal to 0 and find stationary points. And find stationary points. And if you see, the definition of this stationary point is points where f dash of x is 0. Okay. So first, basically, you'll equate f dash of x is equal to 0, and you'll find stationary points. Now, the number of stationary points for a function can be many. See, for example, if f of x is a second degree polynomial, then when you differentiate it, you'll be getting a linear equation, correct? And when you equate, when you get you'll get a linear polynomial. So when you equate this linear polynomial to 0, you'll get only one value for x, which means you have only one stationary point. But now, if your f of x is cubic function, then when you differentiate that, you'll be getting a quadratic polynomial, correct? And if you equate the quadratic polynomial to 0, you'll be getting two values for x, which means there are two stationary points. Like this, number of stationary points depends upon the f of x that you consider. So let me consider one such stationary point, and let me discuss the cases. Let it be x0. Let it be x0. So x0 is one stationary point. Okay. Now, to calculate f double dash of x0. Okay. Now we need to calculate f double dash of x0. See, once you get f of x, you will differentiate that and equal to 0. Then you will be getting a stationary point x0. Then once you get x0, you will be calculating f double dash of x0. Means basically you will be differentiating this function one more time, and you will be substituting that x0 value here to get f double dash of x0. Now there are different cases. If f double dash of x0 is positive, then the function f of x has minimum at x is equal to x0, and the minimum value is f of x0. Correct? Means if the second derivative at that stationary point is positive, then we say the function has a minimum there. Now, why it should be positive? Let us see. Means, for example, if it should be negative, if I write it's negative and if I say minimum, why that condition gets violated? Let us see here clearly. For your convenience, let me draw a graph here beside this point so you can understand the things. Okay. Zero x y, which is f of x. Okay. So now, for your understanding, let me enlarge the diagram for a while so that you can feel the things. Okay. So let us suppose this is the graph. Now I told you if second derivative at a point is less than 0, then if is positive, is greater than 0, then the function has a minimum. So let us see that now. So let us suppose there is a function like this which is having a minimum here. Geometrically, you could sense that. So let us suppose this point is x0. Okay. This point is x0. Now, if I write f dash of x, what does f dash of x mean to me? At f dash of x0, for example, if this point is x2 and if this point is x1, Then when x1, this differences x1 and x2 are very small, we could write f dash of x0 at this point as f of x2 minus f of x1 divided by x2 minus x1, which you have seen in just before minutes. Correct? So f of x2 divided by, f of x2 minus f of x1 divided by x2 minus x1. So if you want to find second derivative, f double dash of x0, what could I write here? F dash means basically if you want to calculate first derivative, you will take the difference of the functions. But if you want to calculate second derivative, you will take the difference of the first derivatives. Correct? So this can be written as f dash of x2 minus f dash of x1 divided by x2 minus x1. This is what second derivative, basically d square f of x divided by dx. Correct? So now let us see what's the value of this when you're having minimum like this. Okay, so now let me use a different color for your understanding. See now, at this point, if I draw a tangent, or let me slightly modify the curve to a bit so our understandings will be clear. I hope there is some issue with sensing. Okay, see here, let me draw this curve clearly for you. Let us suppose there is something like this. Okay, so that it has a minimum at x is equal to x0, and this is f of x1 and this is f of x2 for the time being simultaneously. Okay, so now see here carefully. Let us examine this quantity f dash of x2 minus f dash of x1 divided by x2 minus x1. So now this is f dash of x2. If you draw a tangent here at this point, the tangent could look something like this. Correct? Of course, it's a straight line. So the green line is a tangent at the point x is equal to x2. Similarly, if I draw one more tangent at this point x1. So now if you see, this is how the tangent at this point look like, something like this. Okay. So now if you see, this blue line is a tangent for the function at x is equal to x1, and this green line is a tangent for the function at x is equal to x2. Correct? Now if you see, let me write the data also in same color. This theta2, basically where theta2 is the angle made by the tangent drawn at the point x2 to the curve f of x. So this is theta2. Similarly, if you see, this is theta1. Correct? Because this blue tangent is the tangent drawn at the point x1 for this function, and this green tangent is the tangent drawn at the point x2 for this function. So now if you see, this is equal to f dash of x2 now. Now what is f dash of x2? If you see here, this green line is f dash of x2 here. Correct? So if this theta2 is less than 90, what could be the slope, positive or negative? What could be f dash of x2, positive or negative for this curve? I need your answers here. Okay, f dash of x2. What's the value of f dash of x2? Is it positive or negative? If you have drawn this slope tangent at x2, you got an angle which is less than 90. So tan theta is positive or negative? Positive. Correct? I expect answers from all of you who are on live. Positive. Correct? So if this is positive, minus, now what is slope of f dash of x1? Positive. Yeah, good, all of you. So what is the slope at the point x1? Here you see theta1 is greater than 90. Negative. Correct? So minus negative divided by x2 minus x1. You see x1 is less than x2. Correct? Negative, all of you. Okay, so let us follow here. So if you see x2 is greater than x1, which means this x2 minus x1 sign is positive, which means this difference x2 minus x1 is positive. Correct? So negative of negative will again give you positive. So positive plus positive, the whole numerator is positive divided by positive, which means the answer is positive. Means when a function is having minimum at a point, the derivative at that point will be, the second derivative at that point will be positive, and that's how you see this f double dash of x0 is positive for having a minimum at this particular point. Did you understand? Total result is positive. Maunika, correct? So did you understand why this second derivative should be positive if the function is having a minimum? It's simply because of the tangents that you see geometrically. So now getting back to our analysis again. Yeah, I hope it's clear now. So see here, this is what we have mentioned here. that this f double dash of x naught is positive, and this positiveness comes from this particular diagram. Okay, so this is why for having minimum, you'll equate your second derivative to, you'll find the value of second derivative at that stationary point, and you'll see whether it's positive or negative. Okay, so please take this points till now. Slope of slope. Okay. For example, Praveen, if you see, velocity is first derivative of displacement and acceleration is second derivative of displacement. Okay, so there are quantities defined in such ways. Okay, so see here. Let us go for second case here. See here, this is the first case that we dealt when f double dash of x naught is positive. So similarly, we'll see what's the case when f double dash of x naught is negative. Yeah, we have time for that. Before going for that, let me ask you one important question. I told you, or many of you might have experienced, if you want to find a maxima or minima of a function, you equate the derivative to 0. Means you know something, or from Rolle's theorem that we discussed yesterday, if there is an extremum point, if there is a maximum or minimum, definitely at that point derivative is 0. Correct? This is what we have discussed. Now I'll ask you one question, try to answer that. If at a point if derivative is 0, is it mandatory that the function has an extremum at that point? Means if, for example, you know, if there is an extremum, derivative is definitely 0 at that point. Now if derivative is 0 at that point, is it mandatory that the function has an extremum at that point? No, it's not mandatory, because I'll give you examples in short course. No, yes, of course, I am happy that all of you are answering it correct. If derivative is 0, it's not mandatory that the function need to have an extremum. Okay, yeah, correct, all of you. So please see here, we'll discuss why that's happening after looking at two different cases. B, if f double dash of x naught is negative, then the function f of x is said to have a maximum, at x is equal to x naught, and the maximum value is f of x naught. Now one thing I want to make you to clear here, see, you know, in exams sometimes they'll ask you for this x naught value, sometimes they'll ask you for the f of x naught value. In exam they'll be asking you two kinds of questions. Basically they'll ask you the following function f of x is equal to, then there is some function there, they'll ask you the function has a maximum at, and they'll stop the question. At that time you should not compute till this point, you should compute till this point, and you need to write the value of x at which the function is having maximum or minimum. Now if they're asking you maximum or minimum value of the function, you should calculate this f of x naught. Okay, so please don't lose your marks by doing extra things here. So see, now I hope you can draw the graph of this particular things here. Let me help you out in that. Let us suppose there is a function like this, 0, x and y, and this is y is, okay, let me write it inside. This is the function y is equal to f of x. So now if this is the point where you have maximum, I hope you could draw this diagram along with me since you have exposure now. X naught, let us suppose this point is x2 and this point is x1. Okay, now if you draw the tangents over there, the tangent at this point x2 would look something like this, where this is theta 2, because this is the angle made by the tangent at point 2. Similarly, if you consider tangent at point 1, and if you draw this, that would look something like this. This is theta 1. So now if you consider this value f double dash of x naught, again you have f dash of x2 minus f dash of x1 divided by x2 minus x1. Okay, so if you see here, this x2 means basically this theta 2 is greater than 90. Correct? If theta 2 is greater than 90, then tan theta is negative. Correct? So which means this f dash of x2, basically slope of tangent 2 is negative, minus f dash of x1. If you see at point 1, the tangent that we have drawn here, the angle made by the tangent is less than 90, which means tan theta is positive. Correct? If tan theta is positive, we declare that the slope is positive and we write a positive sign over here, divided by this x2 minus x1 is always positive because we are considering h2 to the right of x1. Correct? So this is again positive. So if you see negative, I mean negative sign of this positive value is negative. So whole numerator is negative, and negative by positive will give you a negative sign. Okay, so that's why this f double dash of x naught is negative for the function to have a maximum at a particular point. Okay, so please take this. Then we'll see the third case. What if f double dash of x naught is 0? The most important case. I hope I'm blocking the diagram. Okay. Clear so far? Any issues? If you see, if you try to remember this, if f double dash of x naught and all is positive or negative, you will feel a bit difficulty over there. But now, if you have some graphs and all, some geometrical background beyond that, in exam you can check in quick senses. Yes, slope is nothing but derivative. Manoj, I have explained it in my second lecture during the concept of differentiation. So please see it. Yeah, Mohan Dev, I hope you are not in my second lecture. So please, whoever is not in my second lecture, please look at here. Slope is nothing but tan theta, where theta is nothing but angle made by the tangent at this particular point. Okay. So Mohan and Manoj, I hope you better go to my second lecture and see the concept of differentiation that I discussed over there. Okay. Yeah, okay, Manoj, sort it out. Now we'll see the third case, which is most important case, because the second derivative test. Actually, this is called second derivative test because we are more concerned with what's the sign of the second derivative. So we'll see the moment when the second derivative test fails. For example, see. Case C. Since we are denoting with ABC, let us make the word C. If f double dash of x naught is equal to 0, means if the second derivative at that particular point x naught is 0, then we can't comment on the existence of maxima and minima at that point. Means with the help of the second derivative test, basically you can't talk about whether maximum is there for that function or minimum is happening for that function, and such points are called points of inflection. Points of inflection. Yes, Praveen, it's correct. First derivative tells you whether a function is increasing or decreasing, and second derivative will give you whether the function has a maximum or minimum. Okay, so for example, if you see example, if f of x is equal to x cube, what is f of x, f dash of x here? This is 3x square. Now, if you equate it to 0 and if you get stationary point, you will get x naught is equal to 0. Correct? X naught is equal to 0. Then f double dash of x. If you write it, f dash of x is 3x square. So what is f double dash of x? It's 6x. And this implies f double dash of x naught. Means if you substitute the stationary point in this second derivative, we have 6 into 0, which is again 0. And if you see f of x is equal to x cube, is not having a maximum or minimum at the point x is equal to 0. Because if you see, the graph of x cube could look something like this, which I would like to give you at this moment. X 0 minus x, y minus y. So now if you try to look at the graph of f of x is equal to x cube, it slightly goes like this. Here if you see at this point, it's almost converging. Okay, like it changes its curvature basically here. So at this point, you got the derivative to be 0. First derivative to be 0, and you got x naught is equal to 0. But if you see, this function doesn't have a maximum or minimum at this point, because as you keep on increasing the values of x, the function keeps on increasing. Similarly, as you keep on decreasing the values of x, the function decreases. But we can't comment on maximum or minimum. It may or may not exist at that point. Okay. Now, similarly, one more thing, I would like to give you one example that we discussed earlier. Could you tell me what's the maximum value of this function? The maximum value of sine x by x. I'm giving you this particular example here to show you again the failing of this second derivative test. If you do carefully, you will be getting again x is equal to 0 as the stationary point for this function f of x. Let me 1, of course, correct. The answer for this is 1. See here, f of x is equal to sine x by x, correct. So what is f dash of x? X into cos x minus sine x divided by x square, and if you equate it to 0, you will be getting tan x is equal to x, for which 0 is one of the stationary points. Means x is equal to 0 is one of the points where this equation gets satisfied. Actually, if you see, there are infinitely many number of solutions for this equation, tan x is equal to x, because the lines y is equal to x and the curve of tan x got cut each other many number of times. Okay, and x is equal to 0 is such one point where this differentiation is 0. First derivative is 0. So if you calculate f double dash of 0, you can try if you want, you will be getting 0, which means your second derivative fails. Your second derivative test fails. You can't tell whether there is a maximum or minimum. But this question was asked 4 times in GATE examination. Okay, and if you remember only this particular process, you're lost, because if you calculate, you'll get the second derivative to 0, and you don't know whether it has maximum or minimum. So that's why I gave you the graph of x. F of x is equal to sine x by x in my first lecture, or in my second lecture probably. You could remember I have given you graph of sine x by x in my second lecture, so that because here at this moment you won't be able to find what's the maximum value of sine x by x using this standard procedure. And if you see, I would like to draw again for the newcomers and all. 0 x minus x y minus y. Now I told you that day, if someone is not there at that moment, I request you to please go to the beginning 15 minutes of the second lecture, which was in engineering sub channel. You can go over there. So first of all, these are the lines y is equal to 1 by x and y is equal to 1 minus 1 by x that we draw on that day. Correct. So now the graph of sine x is something like this that we have drawn the other day. So this is how graph of sine x by x looks like, which we have also drawn that day. So if you see, the maximum value here could be somewhere 1. Actually, it's 0.999 of that order, but we want of generally things. So we say the maximum value is 1. This standard procedure fails for this sine x by x example. Okay, so that's what we see in basically dealing with this second derivative test and points of inflection. And I also asked you, if derivative is 0, can maximum or minimum exist at that point? It's not mandatory, because here you have seen f of x is equal to x cube at x is equal to 0. The first derivative is 0, but the function doesn't have a maximum or minimum at that particular point. Okay, clear? So these are some some basic background how to find a maximum or minimum of a single variable function. Mechanical students, if you remember, and civil engineering students as well, if you remember, while drawing shear force diagrams and bending moment diagrams, SFD and BMD, you will be getting the maximum bending moment at the points where shear force is 0. Correct? If you remember that, I would not like to go into details, because since all department students are here, but generally you'll get maximum bending moment at the points where shear force is 0, because the shear force is nothing but differentiation of bending moment. Okay, so all these things are here. So before closing today's lecture in next 5 minutes, I would like to give you 2-3 important things that is really in need for solving tomorrow's examples. The maximum value of A cos x plus B sin x plus C is, or in fact you can write a range. The range of A cos x, the range of f of x is equal to A cos x plus B sin x plus C is C minus root of A square plus B square and C plus root of A square plus B square. Okay. Yes, maximum value is C plus root of A square plus B square and minimum value is C minus root of A square plus B square. This result is of some importance because questions came in gate based on this, and if you know this result, your answers could be in a very short moment. And I would like to tell you one more thing. If A comma B are two positive numbers, if A comma B are two positive numbers, then arithmetic mean is equal to A plus B by 2. Geometric mean is equal to square root of AB. And one thing is arithmetic mean, which I call it as AM, is always greater than or equal to GM. Geometric mean. This result is also important because they'll be asking you some functions which are associated in this way, and they'll ask you what's the minimum value of this arithmetic mean. Since this arithmetic mean is always greater than or equal to geometric mean, the minimum value of this arithmetic mean is nothing but geometric mean of the things involved here. Okay, so that's the case. So it's 9:12. Okay, so since today's lecture is planned only up to 9:15, I would like to give few things before going for problems in next lecture today. See here, this concept of maximum and minima is really important, and from the beginning to this point, if you have any questions, you can ask me at this moment. Yeah, inequality, both of them are unequal, Rahul. So from the beginning of my lecture to this point, if you have any difficulties, you can write it in the comment boxes. I would like to study them and I would like to revert back to you. And I advise you, if you don't understand something at this particular points, please visit previous lectures and I would like to give you some suggestions over there. Okay, and if you are liking the content, please do like and share the video and subscribe to channel so that you will get continuous notifications whenever we are launching some lectures. Okay, that's from my side for today. So if you have any, I will give you a couple of minutes since we have a bit time. If you have any questions, you can ask. Manoj, see, why explain failing of sin x by x case once? See, okay. Okay, so see here. If you see, this is how the graph of sin x by x looks like actually. Now, why it fails? X is equal to 0 is one stationary point, correct? Now, this is f of x. Try to calculate f double dash of x. If you calculate f double dash of x, you need to differentiate this particular part, means d by dx of x cos x minus sin x divided by x square here with respect to x. Okay, so if this is the case, if you differentiate this using u by v rule, and that if you substitute x is equal to 0, you will be getting again the thing to be 0, which means you can't define. How did you define the range? Range is nothing but all the set of values right from the minimum value of the function to maximum value of the function. For example, Monica, range of this sin x is from -1 to 1. Similarly, every function has a, if it has a maximum and minimum, we enclose the complete real numbers in a bracket such that left interval is the minimum value of the function and the right limit is maximum value of the function. And for this function, if you want the analysis, I could give you tomorrow why these values are coming: c minus root of a square plus b square and c plus root of a square plus b square. Okay, so please make a note of these things. So I hope we are clear for today's lecture now, and I once again ask you to like and share this video if you like it, so that it could go to maximum people and they can avail this content since it's of free use. Okay. So any questions from your side? Square bracket, where it is? Yes, square bracket, because we involve these particular values. This is the minimum value and this is maximum value. Practice problems, Monica, don't worry. I'll be putting it in the next lecture. We'll solve some questions as we have done in case of limits. After the completion of every concept, I'll be backing up the lecture with some problems that we have. Okay. Practice problems, I'll upload the link shortly. Once we'll get completion of the chapter 1, we'll upload the links of that. Okay. If some of you feel that, yeah, I'll stay safe. Thank you, Mohan. And if some of you feel that I am going a bit fast, you could slightly reduce the play speed of your video. But my intention is to cover some good content in every lecture so that you can get the maximum use of the time. Okay. Yeah, Deepak, you can ask me. What's your doubt? Please be quick. We don't have enough time here today. Yeah, at inflection points, limit and derivatives exist, but they are zeros. That's what we call as inflection point. Correct? Second derivative to be zero, not inflation, inflection. Okay, please correct that. Okay, then whoever is having any issues, you can write it in the comment box. I'll be replying. Please look here. Okay, thank you. Then we'll be closing today's lecture. Meet you all at 7:45 a.m. tomorrow. Thank you.